Hello, and thank you for joining this course again. I'm Katharina Glomb, and I'm a postdoc, and I just recently, well, I didn't move physically to Berlin, but professionally I moved to the Charité to work with Peter Ritter in the section Brain Simulation. So I'm more of a theoretical person, computational neuroscience, and today I want to give you a little bit of an introduction to Connectome spectral analysis and to show you what that is all about. And yeah, so far you've already heard a lot about networks, networks that consist of nodes that are connected by edges. And we've heard from John, for example, about things that you can do to characterize networks, like looking at their modularity or looking at small world networks. And we've also heard about functional networks, where these edges are defined not by physical connections, but by statistical dependencies. And we just heard a lot about how nodes influence each other over time. So these are all very important aspects of brain function and of network neuroscience. So, but now we're going to switch gears a little bit, and I'm going to show you a little bit of a different angle, like a different point of view on signals on networks. So I just want to emphasize that this is like a complementary approach that allows you to think about maybe this kind of signal, like brain data, in a bit of a different way. So the crucial point here, and this may seem obvious, but bear with me here, is that there is a distinction between the underlying graph, like the structure of the graph with its nodes and the edges between the nodes, and the signal that plays out on this graph. So the graph itself doesn't change over time. The nodes remain the same. They remain in the same place, like the brain regions. The connections between remain the same. And the signal on this graph is what changes over time. So for example, here in this illustration, this is just illustrated by the graph keeping its shape and the nodes changing their intensity, for example. So this can be any kind of signal that you've measured from those brain regions that the nodes stand for. And what may seem trivial at first is actually something that allows you to treat this brain data as a graph signal. And you can then use a huge toolbox of methods that is provided to you by so-called graph signal processing. So this is much more of a signal processing point of view. To be a bit more concrete, to give you something to think about and to imagine, let's stick for now to a situation where the underlying graph is made in the way that we've heard about before, which is that you take a structural brain image and you get your brain regions. So these are your nodes, and you do diffusion MRI and then fiber tracking and a lot of different steps in between that we've heard about. So you get your white matter tracks and you build your graph from this structural connectivity. And let's now just imagine that then we measure EEG. We use an inverse model that we've also heard a lot about to estimate brain activity in the same brain regions that we've estimated up here, that we've computed up here. And this is our graph signal. So we have our graph and our EEG signal. And this kind of point of view is also what is important for modeling. And I just want to mention this in view of the upcoming lecture. So here the idea is that these signals, of course, like the relationship between these two entities, let's say, is that we assume, as David also described, that the brain activity spreads through the network along the edges that we've defined. Okay, I said that now we look at this in terms of signal processing. And maybe the most basic, or at least one of the most basic tools in signal processing is the Fourier transform. So the idea that you have a signal that is defined on a domain, we usually don't think about this domain, but let's say you just have a one-dimensional signal that you've recorded over time, and you can decompose the signal into waves or cosine waves of different frequencies. So that's illustrated over here. Now your signal is on a very different domain. It's an irregular domain, and it's not even a continuous domain, because you can't really even say what the distances between these nodes are. So you have this very special domain, which is the graph. But as it turns out, and as we will find out more, and I will tell you a little bit, and then Joanne will tell you later a lot more about it in the tutorial, you can do something that is really completely equivalent to this idea in this situation where you have the graph. So you apply the same kinds of methods that are summarized in this magical arrow, and you end up with patterns on this graph that you can project back onto the brain. I'll show it to you in a bit more detail, but for now, I just want you to know that the equivalent to these kinds of wave patterns can be computed for the brain, and they also form the Fourier basis functions of this graph domain, and they're called harmonic modes. And if you read papers about this, they're sometimes, or like, they're often called connectome harmonics. So you can see these beautiful patterns that you can use as building blocks. And you can then use, just get more comfortable. Okay, so if you look at brain activity in this way, then you can understand any activity pattern that you measure on the brain with any kind of method, so let's say EEG, as a superposition of these building blocks that you've extracted in the same way that you get cosine waves. So you have an activity pattern and you describe it as a superposition of your building blocks weighted by some coefficients. So you have n coefficients, and you can collect all these coefficients together into a spectrum. So this is, again, completely equivalent to a Fourier spectrum, just that here you have a spatial pattern that you're trying to describe. And usually we use Fourier analysis in time, right? I'm just going to show you a little bit more about that too, so you can kind of make this domain switch. But so you've reduced your activity pattern on the brain in each brain region into this graph spectrum. And these are completely equivalent. And to come back to the picture that I showed you before, so your activity pattern is your graph signal. So that's this varying thing down here, the signal that you measured in time. And the harmonic modes are building blocks from the structural graph. So in this way, this approach is multimodal and allows you to combine modalities in ways that are complementary and a little bit different to what we've seen before. And what I'm just going to mention here, and I'm not going to go into this now, I think we're going to learn more about this later in the tutorial. So here is just one activity pattern at some time t, can be resting state, can be task, anything. But you can, of course, do this decomposition for each point in time of your signal that you've recorded. And then you can have a time series of these graph spectra that you can then analyze. Okay. Before I go a little bit more into detail of how you compute this and what is this mathematically, I want to give you a little bit of a physical interpretation of what harmonic modes are. Because at least in my opinion, yes, they're a very useful tool that you can use to analyze your data, but they also have this fascinating connection to pattern formation in nature. And maybe this will also make it a little bit more clear this switch between the temporal and the spatial domain. So I think the violin is a really good example for this. So think about playing the violin. You bow a string and it will vibrate. And of course, first we think of the tone that it makes, but try to think of the shape of the string, because the string also physically vibrates. And it does so in a standing wave pattern. And these standing wave patterns also in space have distinct frequencies, spatial frequencies. Another example for this kind of mechanical vibration are the so-called Chladni plates. Maybe you've seen a video of these. If not, I really recommend Googling this on YouTube. So what happens here is that you have a 2D domain, so a metal plate in a certain shape, and then a sound is played with a microphone, like a pure tone, and the plate starts to vibrate. And because there's sand on this plate, these are the lines that you see here, the sand will collect in the parts of the wave that doesn't move. So the nodes that in the violin you can see here. And they form these patterns, and the pattern depends on the frequency of the tone that you play. So there's this relationship between the tone that you play and the spatial shape that you get. And these are mechanical vibrations, but this goes beyond just these kinds of waves in the strictest sense of wave. If you have a system where chemicals diffuse, for example, you can explain, for example, the patterns that you find on animal coats by modeling a diffusion process on something like this cone-shaped tail. And this is something that has been done for a while. So this is not super new. To go to the brain, show you a few examples of this idea, how it has been applied to the brain. So here we have ocular dominance patterns from the macaque monkey. This has already been described in 1980, and this is also a really fascinating paper where Swindell proposes such a diffusion model that I just mentioned that can explain the ocular dominance pattern that he found in visual cortex. And specifically for EEG, it's not a new idea to assume that the oscillations in the brain or the electromagnetic activity forms these standing waves, and that these waves can in part explain the observed topographies on EEG and MEG. So you can see that there's, well, of course, this is a paper, so they made it pretty, but there's a pretty good correspondence at times between the patterns that you measure and theoretical waves. And you can also use this for structural connectivity in this paper by Robinson from 2016, where they showed that if you compute these kinds of harmonic modes on a sphere and you project them back onto the brain surface, you also get patterns that resemble known macroscopic networks. So I hope that this will convince you that this principle of harmonicity and harmonic modes is something that describes pattern formation in many situations in nature, including the brain. So it's irrelevant for neuroscience in some way. Just have to find out how. So yeah, what I want to say with this is that harmonic modes are a tool, but harmonic modes also link the brain with other phenomena in nature, and that's important here. So to link it to the violin, the vibrations in the brain of brain activity are kind of equivalent to this kind of physical phenomenon of a standing wave on a violin string, for example. And just as a little brain teaser, I want to point out the connection again between the vibrating string in space and the tone that it elicits. So if you want to understand brain activity, you want to understand the spatial organization, but we've also heard a lot about oscillations and spectral dynamics. So harmonic modes can link these two things. And if you think about the fact that on a violin, you will play tones one after another to play music, then you could think that this could also be interesting to understand temporal dynamics in the brain. Okay, now just a little bit about what these harmonic modes really are, because I think for now it just seems like a bit of an airy concept. I keep talking about how you can get them from a graph. And here you don't need to understand all the details. Basically, the most important thing that I want to tell you here is that it's quite simple. So you start with your graph, which is the same as the structural connectivity matrix that we've seen many times before. So you have your brain regions and your connections between them. You compute the so-called graph Laplacian, which sounds fancy, but and there are many possibilities of how to make this step here, but it's really easy. So essentially, you have your weights that are the same as before. Maybe they are normalized, maybe they are binarized, but essentially they just come from these connections. And then you have some kind of degree, sum, or weight in the diagonal. And then you just do a simple eigenvalue decomposition. So that's really a basic technique. And what you get out of that are these eigenvectors. And this here is just to illustrate that the eigenvector can be projected back onto the anatomy, and these are equivalent illustrations of the same thing. So each entry is a brain region, you project this back onto the brain, and this is how you get these fancy looking patterns. And you can, of course, also put it back in this graph shape, and then this can give you more of an impression of how the graph is structured. So you can see the first one is really smooth and kind of just gives a summary of how much each node is connected. Then the second one kind of divides the brain into front and back, and you can also see this in the graph equally. The next one does a division into left and right, and again, you can see this more or less on this graph. It's not perfect, and it goes on like this. And just to summarize a few basic facts here. So you have to, this is not as universal as the Fourier transform that you know from the linear signals, because each graph has its own set of harmonic modes. So every time you compute a new graph, you need to compute a new set of harmonic modes. And then there will be as many harmonic modes as there are brain regions, because, as I said, it's an eigenvalue decomposition. So nothing new there. And they are ordered by graph frequency or smoothness. So to bring back this picture once more, with the violin, you have the same. So the higher the tone, the smaller also the spatial patterns, like the nodal areas of these standing waves will be. And of course, it's not a regular domain, so it's not as easy to spot, but it's the exact same idea. So the brain will be divided into smaller and smaller patches of cortex. So you have hierarchical networks, if you want to interpret these as networks, because they are ordered by their eigenvalue. And you have multiple scales. You start from something very smooth, just front and back, just two parts, for example, to something that is more, that is smaller, divided into smaller parts. All right, okay, I think this is already it. Just to give you a little summary. Brain data can be seen as a signal evolving in a graph and can be analyzed with graph signal processing. So I just gave you a little glimpse of what graph signal processing is. Importantly, or at least I think it's important and fun to think about the fact that harmonic modes explain self-organized pattern formation in many contexts, like animal codes and stuff like that. And harmonic modes are the graph equivalent to cosine waves in Fourier analysis, and they're hierarchical, they're multi-scale, and they're potentially multimodal if you combine, for example, structural connectivity and the EEG signal. So I know that this is maybe a very strange concept. I try to convince you that it's actually easy to compute, but maybe you still have many questions. So I left some space for questions. If you have more questions after the summer school, after the course, you can, of course, email me, or you can try to find me on Twitter. And once you get this presentation, you can look up these papers. That there's, of course, many more, but I don't know, put the most prominent ones that were featured in this presentation. All right, thank you.